Get started today. All right. Before I start, remember that the goal for this week, although it may not happen, is to finish everything, finish chapter 9. If we don't get through quite all of that, then we'll push off some of it till Monday. We have Monday as sort of an extra day to do whatever. So like I also said last week, for a week from today, Monday, I will likely have some, if not all of the 50 minutes here to talk about anything that interests you, which should ideally be chemistry related. And so if you have any questions from previous parts of the course that you want, or things that you think I should cover in more detail, please let me know in advance and I'd be happy to do that. That of course depends on whether we get through everything this week or not, which is the plan. All right, to be very clear too about what's happening today, slides 2 through 5 that we cover today, which will be what are called network solids and network covalent compounds, those are going to be fair game for exam 3. Anything that has to deal with ionic compounds, we won't worry about until the final exam. All right, so today we're kind of wrapping up a few things that are going to be on the third midterm, but then the rest of everything that we do today and everything that we do the rest of this week will all be on the final exam only. Okay? All right, so hopefully that's clear. So last time we talked about metallic solids. We previously discussed the bonding in metallic compounds, which is that delocalized sea of electron model that we discussed. And then last time we also, in more detail, talked about the structure of metals, the different cubic and hexagonal structures that they can take on. So what we're going to talk about today are the two other kinds of solid compounds, network solids and ionic compounds. The first one, we're not going to really talk in detail about the structures, but we want to know the definition and then some properties of their electronic structure, which is the arrangement of the electrons in these compounds. So network solids are basically huge covalent compounds. So they're extended solids, which means they have an infinite structure. There's no real boundary to them, per se. And this should be extended. So they're extended solids, but they're formed by covalent bonds. All right, so remember, metallic structures are formed with metallic bonds in between all the atoms, which are slightly different. But here we're talking about compounds or elements that have covalent bonds. And in some way, they can be thought of as infinite molecules. All right, so far in this course, we've only talked about, for covalent compounds, molecular compounds, which are ones where you have very obvious discrete building blocks, like CH4 is a carbon with 4 hydrogens, and then you have, that's it. But a network solid can be thought of as a covalent compound that just goes on and on and on forever, where the atoms, there's more and more atoms bonded to each other, and they tend to have very regular structures. At least the ones that we're going to talk about in most detail have regular structures. So there's two types of network solids. There are some that are elemental, that only have one type of atom, and then there are network covalent compounds, which have 2 or more different types of elements in them. So 2 elements that are classified as network solids would be the 2 forms of carbon, diamond and graphite, which we've already discussed in a little bit of other context. So there are 2 major structures for carbon. They're both considered network solids because they both have carbon atoms bonded to each other in all directions for essentially an infinite structure. So we have diamond, which is a tetrahedral structure. So if we look at any carbon atom in diamond, like this one, it has 4 other carbon atoms bonded to it, but it doesn't have regular molecules that have a certain number of carbon atoms. It just extends in all directions. So we're just showing a small piece of it here, but in reality this top carbon atom will be bonded to 3 others, and all these other terminal carbon atoms will be bonded to 3 others in all directions. It would go on for a really long time. Now because the carbon is tetrahedral in diamond, that of course means that they're sp3 hybridized. And they have all sigma bonds because they're sp3 hybridized. There's no pi bonding in diamond. Now the other major form of elemental carbon is graphite. This is the more stable form, as it turns out, by a little bit. And in the structure of graphite, you have hexagons of carbon. So you have these hexagonal rings of carbon, and they're all fused together. But they have more of a 2-dimensional structure, because you have these sheets of carbon, and then the sheets are stacked together through non-bonding interactions, through intermolecular forces. All right, so you have these sort of hexagonal sheets of carbon. They're linked in all directions, in 2 dimensions anyway, and then you have these 2-dimensional sheets that stack together to form the structure of graphite. And they, as you'll notice, each carbon only has 3 other carbons bonded to it in this case. So each one is going to be sp2 hybridized instead of sp3. And because it's sp2 hybridized, you have both sigma and pi bonding. And this is another example, like we talked about in the molecular orbital section, of delocalized pi bonding. So each carbon has a perpendicular p orbital that's going to overlap with all of the other ones in the ring to form sort of this delocalized pi interactions above and below the plane. So all the pi electrons are delocalized. They're not localized between pairs of carbons, but they're delocalized over the entire structure. And so clearly these 2 forms of carbon, these have very different structures, and we're going to get into them in a little bit, what the difference is in their properties. So when you have 2 structures of the same elements, you call those allotropes. We've talked about isotopes, which are different atomic structures that have different numbers of neutrons. Allotropes are the same element, but they have 2 different structures. So 2 forms of the same element. So that's a word that you might see, but basically diamond and graphite are 2 allotropes of carbon, and because the bonding is so much different in these are sp3 with only sigma bonds, these are sp2 with delocalized pi bonds. Because the structure and bonding is so different, it stands to reason that the properties are different. So let's look at how the properties of these 2 compare, and these are going to relate then to the structure that I just showed you. So as we know, diamond is very hard. It's one of the, if not the hardest substance known, at least naturally occurring for sure. A very hard substance. It should ideally be colorless. If you buy a diamond that's not colorless, you may have gotten ripped off depending on how much you paid for it. And then also, diamond is an insulator. So if we talk about the electrical conductivity properties, diamond does not conduct electricity as an insulator. However, carbon, in its other form, graphite, looks a lot different. So graphite, if you've ever played with it, is soft and slippery. And that's related to the layered structure. Okay, because those layers are held together by relatively weak intermolecular forces, so the layers can sort of slide over each other. That gives it that slippery texture, and then also makes it a lot softer because there aren't those strong interactions in all 3 directions. There's just the strong bonds holding the sheets together, but the individual sheets are stacked together pretty weakly. Graphite is black in color, so it certainly wouldn't make a very pretty engagement ring like diamond does. And then, if you turn it in terms of electrical properties, it's a conductor. Okay? So it conducts electricity very well, and that's related to the delocalized pi electrons that it have, where the charge that carries charge through those delocalized layers. So if we want to explain these differences, we're going to introduce what's called band structure. So this is going to tell us sort of an idea of how the bonding works in these extended solids. So we talked in chapter 4 about molecular orbital theory, which is if you take 2 atoms together, you form bonding molecular orbitals and anti-bonding molecular orbitals. Well, what happens if we bring thousands of atoms together and make these extended structures like diamond and graphite? How does that work? So when you have extended structures, you still get bonding molecular orbitals and anti-bonding molecular orbitals, but you have a lot of them because you have a lot of atoms that you're combining together. So in that case, what you get are sort of bands of orbitals, which are a bunch of bonding orbitals that are really close together that form almost a continuous band, and then a bunch of anti-bonding orbitals that are higher in energy and also form more or less a continuous band because the orbitals are so close to space because there's so many of them. So if you have an insulator like diamond, and most nonmetals are insulators, graphite's sort of a rare example of a nonmetal that's a conductor. Most of our conductors that we have are metals. Sorry, most nonmetals are insulators. Whoops. So if we have an insulator type structure, if we look at the molecular orbital diagram with energy going from bottom to the top, you're going to have a bunch of filled molecular orbitals on the bottom. These are going to be typically your bonding combinations. Remember, we filled the orbitals lowest to highest. We call these filled orbitals the valence band. That's the name that we give them when we're talking about an extended band structure. And then when we have the antibonding orbitals in an insulator, they're separated by a pretty large energy difference. So you're going to have another band, which I'll show in red here. These are empty. Molecular orbitals, we call that the conduction band. All right. And the point is, when you have an insulator structure, you have a large gap between the filled and the empty molecular orbitals. Because to get electrical conductivity, you need electrons to move from the valence band into the conduction band. So whenever you're conducting electricity, the electrons are hopping around from atom to atom, and the only empty orbitals are the ones up here, so the electron has to go from a filled orbital to an empty orbital to be able to hop along through the structure and to be able to conduct electricity. So when you have a large gap like this, you tend to get an insulator because there's just too much energy for this electron to overcome to move through the structure. Now in contrast, if you have a conductor, so we'll draw that over here, which are going to be metals or things like graphite, the band structure looks a little bit different. So you still have your filled molecular orbitals at some energy level. And again, those are typically the bonding combinations that are going to be filled. But then your empty molecular orbitals, the conduction band as we call it, is going to be right on top of those. You essentially have no gap. So when your band structure looks like this, where the filled and empty molecular orbitals are right on top of each other with no gap, you have what's called you have a conductor because the electrons have no barrier. They're able to very easily move between the valence band and the conduction band and translate through the structure. And hopefully this difference between graphite and diamond makes a little bit of sense now, because if we have in diamond we have all sigma bonds, so we're going to have sigma bonding orbitals, sigma star antibonding orbitals. As we talked about in molecular orbital theory, those tend to be farther apart because sigma is a stronger interaction. Whereas for graphite, we have a lot of pi and pi star molecular orbitals. Those are going to be closer together because pi interactions are weaker. And furthermore, when you delocalize them like you have, they're going to be right on top of each other. Is there a ring in here, or is that just me? I'm going nuts. Okay. Sounded like it was an empty room all of a sudden. All right. Forget that I said that. I'm okay. So the filled molecular orbitals and the empty molecular orbitals are right on top of each other. When you have these delocalized pi orbitals, there's a smaller gap between them, and so they sit right on top of each other and you're able to conduct. Okay? So these are the difference in the band diagrams between insulators and conductors. Now we also have a class of elements that sort of fall in between, and these are called semiconductors. So semiconductors are going to be most of the group 14 elements, so the ones that are the same with carbon. So I'll pull up the periodic table real quick. So carbon, as I said, is either an insulator or conductor, depending on what form it is. But most of these other ones, silicon, germanium, they form what are called semiconductor structures. I think arsenic does as well. A lot of these elements that are sort of the metalloid types, the ones that are right along the staircase, they form what's called a semiconductor type structure. And the classic examples are silicon and germanium. Those are the ones that are the most well studied and well known. And in this case, they're kind of in between. So the band diagram, you're going to have a valence band and a conduction band like we did before, but there's going to be sort of an intermediate gap. It's not a huge gap like you have in an insulator, but there is at least a small gap. All right, so you have your valence band, then you have a small gap, and then you have your conduction band. Maybe that's a little bit too small, but that's okay. So that's our conduction band. All right, so the two don't sit right on top of each other anymore, so there is some barrier to conduction. The electrons have to go to higher energy. So there's an intermediate gap. And unlike metals, the conductivity increases with temperature. That's not going to be a real big deal for us, but because we have this sort of intermediate gap, if we heat up the semiconductor, more of the electrons have enough energy to hop over this gap and go into the conduction band. Remember, conductivity is all about electrons moving from the valence band to the conduction band and then translating through the structure. And when you have this intermediate gap, if you raise the temperature, you're going to have more electrons that are able to do that. And so you get higher conductivity as you increase the temperature. So that's a big difference and an easy way to distinguish between a conductor and a semiconductor. When you have a conductor, the conductivity decreases with temperature for more physics-based reasons that we're not going to talk about. But when you have a semiconductor, the conductivity increases with temperature. There's a difference there in that behavior as well. Now, semiconductors are a very important class of materials. You've probably heard of solar cells, photovoltaics, those sorts of things. Those are all made from semiconductors where they absorb light, and then the absorbed light energy is converted into electrical energy. And semiconductors are sort of the types of materials that we use for that. So because of that, there's been a lot of research in terms of how to make better semiconductors. And what's been discovered and known for a long time is that you can do what's called doping to take a semiconductor and make it even better. So there's two types of doping, N-type and P-type. And basically what you're doing when you're doping is you're taking the native semiconductor like silicon and you're adding in a small amount of another element that's going to change the number of available valence electrons. So when you have an N-type doping, you dope with extra electrons. And so an example of this would be if we start with silicon, which is in group, what's the group, 14? Or I guess we're going to call it 4A. We're using that nomenclature. So group 4A is silicon. It has 4 valence electrons. If we dope silicon with something that has 5 valence electrons, a classic one that people use is arsenic, As. If you dope it with something that has 1 more valence electron, you're giving the system a little bit more valence electrons. Now, doping is a very small percentage. It's not that we're adding in a ton of arsenic, but just a very small percentage of arsenic doped into silicon gives us what's called an N-type semiconductor. And the reason that this works, and the reason that it gives us better semiconducting properties, is that we have our valence band and our conduction band separated by some gap. I'll sort of exaggerate the gap here to show you how this works. So our valence band and our conduction band but then what happens is if we put a little bit of arsenic in here, arsenic has extra electrons. So if we fill all of the valence band orbitals in silicon, if we have some extra electrons there from arsenic, we have to put them somewhere else so that those extra electrons are going to occupy orbitals that are either in or very close to the conduction band. So your extra electrons are going to end up very close to the conduction band. And so we've effectively shrank the gap and made this into a better conductor because now the electrons are closer to the conduction band, and some of those mobile electrons, as we call them, are able to more easily transport into the conduction band. So when you do N-type doping, you're adding in extra electrons. Those extra electrons end up close to the conduction band and result in higher conductivity. Now you can do the opposite, which is doping with fewer electrons. We call that P-type doping. So the other example is P-type, which is doping with fewer valence electrons. And again, when we talk about doping, we're talking about very small amounts. So I don't know what the exact percentage people are, but for arsenic doped silicon, you're putting in only a fraction of a percent of arsenic. It's not a lot of arsenic that you have to put in there. Just a little bit to make some mobile electrons close to the conduction band. And for P-type, we do the same thing, but we use an element that has fewer electrons. So if we take silicon and dope it with boron, for example, that would be boron-doped silicon. So here silicon has 4 valence electrons, boron has 3. So if we're putting in a few atoms into the structure that have less electrons, what's going to happen is that when we look at the band diagram for this, our valence band is no longer going to be completely filled. All right, because in silicon the valence band is completely filled. We add in some elements like boron that has fewer electrons than that, so you're going to have to take some electrons out of the valence band, and so you get these sort of positive charges in the valence band, these vacancies as we call them, or holes. All right, so you're going to get some positive charged holes in the conduction band. In the valence band. You're still going to have your conduction band way up here. And in this case, when you have a P-type semiconductor, all of the conductivity takes place formally in the valence band because you have electrons in the valence band that are able to move into these holes that are left behind when you dope in boron. The conduction band in this case is not involved at all. So you have these holes in the valence band, the electrons move into those holes, and that's responsible for the conductivity. All right, so that's sort of a little bit of a primer on electronic structure of semiconductors, which again relates directly to molecular orbital theory. The last thing we'll talk about with network solids are network covalent compounds. And for this, we just want to be able to recognize an example of a network covalent compound and what it means about the structure. So let's think about carbon dioxide versus silicon dioxide. Now we know from many examples in this course that carbon dioxide has a linear structure with 2 carbon-oxygen double bonds. Right, so it's going to have this structure here. 2 sigma bonds and 2 pi bonds in total. And we know that it's a nonpolar gas. But what about if we consider SiO2? So let's just replace carbon with silicon. Silicon is just one element directly below carbon on the periodic table, so we have the exact same number of valence electrons, all of those things. We get something very different in this case. So the issue here is that silicon has 3p instead of 2p valence orbitals, and those 3p orbitals form very weak pi bonds with oxygen. So it's much more favorable. Remember that when compounds form, they want to form the combination that gives the strongest bonding. If the pi bonds are very weak for silicon, we're not going to form a structure like this that has silicon double bonded to 2 oxygens. Instead, what's better is if silicon forms 4 sigma bonds instead. So you get what's called a network covalent compound that has covalent bonding going on and on and on in all directions. So you start with a tetrahedral silicon with 4 sigma bonds to oxygen. Now formally this is going to have a 2- charge because it's silicon with 4 singly bonded oxygens, but then these oxygens are bonded to other silicons in all directions. So there's another silicon there, silicon, silicon, and so on. So then this goes to another silicon, which is tetrahedral. That goes to another one, the tetrahedral, and it just goes on and on and on forever. So it's another example of a network covalent compound, which is formed by covalent bonds, but they go on and on and on in all directions forever and ever, effectively. Okay, so this structure just goes on to build a large crystalline structure. All right, so it's a network covalent compound where instead of like diamond, where we have just one type of atom, or silicon by itself, which is just silicon forming a network structure, here we have silicon and oxygen forming covalent bonds and forming a network type structure. All right, so these tetrahedra, these SiO4 2- tetrahedra extend forever, but in net it's a neutral compound because each one is bridged to another silicon atom. All right, so the smallest building block is an SiO4 2-, but then as you bridge those to other and others, more and more silicons in all directions, in total you're going to end up with a neutral charge with the empirical formula of SiO2 once you extend out the structure. So the differences are quite marked. So CO2, as we said, is a gas. It's a nonpolar gas. SiO2 is a hard, brittle solid. So it's hard, but it can be crushed under the right conditions. So that's what we mean by hard and brittle. They don't mean the opposite things. And SiO2 is a very common substance for us in our everyday life. So sand is largely composed of SiO2. Glass is an amorphous form of SiO2. And both of these common substances contain these types of building blocks, these network structure with silicon and oxygen, silicon oxide tetrahedra extending in all directions. All right, so that's an example of a network covalent compound. And we just want to be able to recognize what it means to be a network covalent compound and also how some of these properties depend on it. So this is clearly nonpolar gas because it's discrete CO2 molecules. This one becomes a hard, brittle solid because now we have these strong covalent interactions holding everything together in all directions. So you have a much different type of physical property when that happens. All right, any questions on that before I move on to the new stuff? So the new stuff we're going to do, which again, we're not going to cover any of this future stuff on the third midterm. This is all final exam stuff now. We have to talk about ionic solids now. So this is the last major category of solids that we're going to deal with in this course. So we've talked about ionic compounds, many different properties of them. Most recently, we talked about lattice energy. So we know we have some insight into how ionic compounds form and the interactions between the ions and things like that. But what we're going to talk about today is in detail how the structures of them actually look like in the solid state specifically. All right, so just a little bit of review about how they're held together. Remember that ionic compounds have discrete ions, and they have very strong forces of attraction that hold them in place. So the ions are held in the structure by these strong charge-charge interactions. We call these Coulombic interactions when they involve charged particles. So we have strong forces of attraction between the opposite charges. And the structure that we observe for ionic compound is the one that's going to maximize the attractive interactions. So the ions are going to arrange themselves in such a way that the attractive interactions between positive and negative charges are maximized, while also minimizing the repulsive interactions. So if you bring the ions too close together, the negative charges are going to start repelling each other, and the positive charges are going to start repelling each other. So you have to sort of this balancing effect of maximizing attractions and minimizing repulsions. That's going to be, anytime we form an ionic structure, that's going to be the idea. All right, so that's what's happening, and then what exactly do these structures look like in more detail, or how are they formed? So whenever we have an ionic compound, we have two ions. One of them is going to be bigger than the other. I guess by coincidence they could be about the same size, but typically you're going to have a larger ion and a smaller ion paired together. The larger ion is usually going to be the negatively charged one, because as we know, when we add electrons to an atom, the radius gets larger. And the larger ion is going to occupy one of those cubic structures that we talked about with regards to metal. So it's going to occupy one of the common packing arrangements that we talked about last time, which is going to be primitive cubic, face center cubic, or hexagonal close packing. We're really only going to talk about ionic structures that deal with these two, and body centered cubic is another one where we're not really going to have an ionic compound that's built from that. But our ionic structure is going to start with one of the ions, usually the negative ion, occupying the positions of one of these lattices, as we talked about last time. And then the positive charges, the smaller ions, which are usually the positive ones, those are going to occupy holes in the structure. So as we discussed with all of these structures, none of them have 100% packing efficiency. There's always some empty space in there that's not filled by the ions or the atoms. So that empty space is going to be filled by the ions of the opposite charge. All right, so those smaller ions are going to occupy holes in the structure. Now the question becomes, which of these structures do we have? Primitive cubic or face-centered cubic, primarily the two we're going to be debating, and then which holes are occupied. That's going to depend on the nature of the ions. So the observed structure and which holes are occupied depend on the nature of the positive and negative ions. And they primarily depend on the sizes of the ions. All right, so we're going to build up a structure with one of the ions, either primitive cubic or face-centered cubic. We're not going to really talk about hexagonal in any detail. And then we're going to take holes in those structures and fill them with the other ion. And which holes get filled and how many of those holes get filled depend on the nature of the ion. And that's what we're going to discuss today. So there's really only three types of holes we're going to worry about. So let's talk about those holes and how they differ from each other. So the first type is called a tetrahedral hole. And these holes exist in a cubic close-packed layer. So remember that when we form these close-packed structures, we take a layer of atoms and then we place them staggered relative to another layer of atoms. So you have this little dimple here. In the center of this is what's called the tetrahedral hole. So this little gap between the two layers is called the tetrahedral hole. So it's in a dimple of a cubic close packed structure. And then probably the easiest way to visualize it is that you have one of these in each corner of the CCC unit cell. Or sorry, the CCP unit cell. So if we have our face-centered cubic unit cell, which are shown with the spheres here, each corner has a position where it's surrounded by 4 atoms. So it's going to be each corner, there's going to be one there, one in each corner. So we have a total of 8 corners, so we have 8 tetrahedral holes in the structure. So the reason we call them tetrahedral holes is because they're surrounded by 4 of the opposite ions. So you have 3 from the face center and 1 in the corner that are going to surround this ion. So you have this one here, you're going to have another one in this corner, back corner, and all 4 on top as well. So you have a total of 8 corners in the structure, and each one has what we call a tetrahedral hole that's sort of situated there. That one's a little bit harder to visualize, but it's located inside the structure, which is important, and also we can now calculate the radius of this. So determining the relative size of this hole, how big is it compared to the size of the larger ions? Remember that the larger ion is going to be occupying the face-centered cubic positions. We want to know how big of another ion can we fit in there. How big is an ion that we can squeeze in there? So from earlier, we know that the side length for a cubic close packed structure is 2 times radical 2 times r. We're going to use capital R to abbreviate the radius of the larger ion. And again, these derivations aren't so important for you guys to be able to reproduce, just to help you understand where this all comes from. The diagonal of a cube, remember, is going to be a times the square root of 3, which is equal to Alright, so we're just going to replace a with 2 radical 2r. So we get 2 radical 2 times radical 3 times r. And then if we go through the diagonal of one of these cubes, if we think about going to the center here, we go through 1 radius for the larger ion. We go through the diameter of the smaller ion, which resides right there. And then getting us to the center, we go through the radius of the larger ion. So as we go from corner to corner, we go through a total of 4 times the sum of the small and the big radius. All right, that one's a little bit hard to see, I admit it, but we're going from corner to corner here. We go through a radius of the larger ion, we go through the diameter of the smaller, and then the radius of the larger takes us to the center, and then we do that again to get to the opposite corner. So a total of 4 times the sum of the small and the big radii. Okay, so that's the relationship. We solve for this, and we get radical 3 over 2 times big R is equal to r plus r, so we divide both sides by 4. We solve for the small radius r, and that's going to be equal to radical 3 over 2 minus 1 times the larger radius, which is equal to 0.225 r. Alright, so the tetrahedral hole has a radius that's about 22% of the radius of the larger ions. We can fit a cation that's about that size in there. Alright, so that's the limiting size for a tetrahedral hole. Let's look at octahedral holes, which might be a little bit easier to visualize. So octahedral holes are between 2 sets of three atoms. In adjacent cubic close packed layers. So these octahedral holes also exist in the face-centered cubic structure. And if we look at the face-centered cubic structure and where do these octahedral holes end up in the unit cell, there's going to be 1 on each edge, and 1 in the center. Alright, so these little white circles here that have an O in them, those are the octahedral holes. There's 1 in the middle of each edge, and then there's 1 in the center. If we look at the one on the center, it becomes pretty obvious why we call it an octahedral hole. So that one in the center has 1, 2, 3, 4, 5, 6 ions surrounding it, so we call it an octahedral hole. It's at the center of an octahedron formed by the face centers of this structure. But there's a total of 1, 2, 3, 4. There's 12 edges, and then one in the center. So there's a lot of different octahedral holes. If we want to determine the relative size of these, we know that for a face-centered cubic structure, A equals 2 radical 2 times R. And if we go through an edge of this structure here, we have 2 times the larger radius as we go from edge to edge, and then we also go through one of the octahedral holes where we have 2 times the radius of the smaller one. So that's going to be 2 times big R plus 2R. So this time we don't have to consider the diagonal, we just go along one of the edges. 2 times big R plus 2 times little r is going to give us the length of an edge, which is equal to 2 times the square root of 2 times big R. So we just do a little bit of algebra now. We just divide both sides by 2. And then solve for the small radius, which is going to be radical 2 minus 1 times the big radius, which is equal to 0.414 R. So as I'll get into in more detail, this is the limiting size for an octahedral hole, and that makes it larger than a tetrahedral hole. All right, we saw that a tetrahedral hole was 0.225 times the radius of the larger ion. This one is 0.414, so it's a little bit bigger than a tetrahedral hole. And then the last type of hole is a fairly simple one also. It's called a cubic hole. So in this case, for a cubic hole, we're just looking at the center of a simple cubic structure. So the first two holes, tetrahedral and octahedral, exist in face-centered cubic. Now here we go back to simple cubic, and if we put another ion in the center, that's what we call a cubic hole. So we have the larger ions occupying the corners, and then we put the opposite ion right in the center. That's what we call a cubic hole. Okay, so anions on the corner, cation in the center is how it typically works. So in this case, for a simple cubic structure, A is just equal to 2 times the radius, because as we go from corner to corner, we just go through 2 radii of the larger ion. If we go along the cube diagonal now, because we've placed one in the center, A times the square root of 3, which is the length of a cube diagonal, is equal to twice the larger radius plus twice the smaller radius. Again, as we go from corner to corner, we go through 2 big radii and then 2 radii for the center atom, which in this case is usually the positive charge. All right, so then what we end up with is 2r times the square root of 3. We just take a radical 3 and we write it as 2r radical 3 is equal to 2 big R plus 2 little r. So a lot more geometry here, and then we get and the cubic hole is 0.732 times the big radius, so it's the largest one yet. So those are the 3 types of holes that we can have in an ionic compound where the opposite charge are going to sit in one of those holes. Okay, so we saw that those are the limiting sizes of each of the holes. And then the last thing we want to talk about is how to count the holes, okay? So how many of each hole are there in the structure? How many total ions could fit in there? So again, this time we're going to use the rules for counting atoms in a cubic structure. So if we have tetrahedral holes, I'm showing all the tetrahedral holes in this structure, which exists in each corner, but all the tetrahedral holes are completely inside the unit cell. All right, so all 8 of our tetrahedral holes are inside the unit cell. So that means in total we have 8 tetrahedral holes, where if we were to have ions in each of those tetrahedral holes, that would be a total of 8 ions in the unit cell. All right, each of those tetrahedral holes counts as 1. All right, so we'll talk about stoichiometry of these in a little bit, but that shows us that if we have all tetrahedral holes filled, we're going to have 8 of those ions in the structure because they're not shared by any other unit cell. If we go to the octahedral holes, we saw that in the octahedral holes we have 1 on each edge, and there are 12 edges. And remember, when we count edges, what do those count as? 1/2, 1/4, 1/8, what is it? 1/4. So edges are shared by 4 different unit cells. So each of those we count as 1/4. Those are the edge positions. But we also saw that we have one octahedral hole right in the center, which is not shared. So that's our center position. So in total, there are going to be 4 ions that can occupy octahedral holes. If we fill every single octahedral hole, there's going to be 4 of that ion in the structure. And then finally for cubic holes, this one's pretty trivial because we just have one cubic hole and it's in the center. So that means there's going to be 1 ion that can fit into a cubic hole. Alright, so those are the relative numbers of each hole in a single unit cell. So there's 8 tetrahedral holes per unit cell, 4 octahedral holes per unit cell, and if we go to the simple cubic structure, there's 1 cubic hole per unit cell. Alright, and so just like we saw last time, these details, a lot of them are a little bit much for us, so what we really want to be able to do is just learn this table here, which is the summary of all the holes. If you can internalize the information that's on this table, that'll get you through the vast majority of the problems you have to do. Alright, so for tetrahedral holes, we saw that there was 8 per unit cell, octahedral 4, cubic 1. Now in terms of the radius of the ion that occupies them, we calculated the limiting radius by doing those derivations. So what really happens in this case is if we have a ion where the radius is 0.225 r up to 0.414, it's going to occupy the tetrahedral hole. So in other words, that number that we derive, 0.225 r, that's the smallest cation that you can put in there. And then if it goes up to 0.414 r, it's going to still occupy that same position. So it's basically going to stretch out the structure a little bit. It's going to have to force open that hole a little bit. But it's going to go all the way until 0.414 r. But once it gets to this limiting value, that's the crossover where it's going to start occupying octahedral holes. So if the smaller ion is even larger, if it's 0.414 up to 0.732, all right, so again, those numbers that we derived are the limiting numbers, the smaller or the lower end limit. And so if the ion is between 0.414 and 0.732 times the larger radius, it's going to go into an octahedral hole. And then finally, if it's larger than 0.732, it's going to go into a cubic hole. All right, so all those numbers that we derived, 0.225, 0.414, and 0.732, those are the lower limits. If the ion's a little bit bigger than that, it can squeeze in there, it can force the structure apart a little bit and make that hole a little bit bigger to occupy a slightly larger ion. And then finally, the type of unit cell that these come from, remember that the tetrahedral and the octahedral holes exist in a face-centered cubic unit cell, whereas the cubic hole exists in a primitive cubic or simple cubic unit cell. Alright, so that's all the important information about the holes. So now what we're going to close up with is just some examples of real ionic compounds and how they're built up by filling these different holes in the structures. Alright, so if we have sodium chloride, probably the most well-known and one of our favorite ionic compounds, we look at the ionic radii of each ion that's involved first, and that's going to help us predict what the structure is. So sodium plus has a radius of 102 picometers. Again, this is not information you can derive. It would be given to you if you need it. And the radius of the larger ion, which is Cl minus, is 181. Alright, so we have ions of 2 different sizes, and to figure out which structure these are going to occupy, we have to take the ratio of the two. So the ratio of the smaller ion to the bigger ion is 0.56 when we divide those two. 102 divided by 181 is 0.56. That's in between 0.414 and 0.732. And so that from the table on the previous slide tells us that the sodium ions are going to occupy octahedral holes. Alright, so whenever the ion is in between 0.414 and 0.732 times the larger ion, here it's 0.56, it's going to fit into the octahedral holes. So then the question becomes how many holes are filled. So in a face-centered cubic structure, remember that we have, that's going to be where the chloride ions are. So the chloride ions are in green, they occupy the face-centered cubic lattice. There's 8 corners that count as 1/8. There's 6 on the faces that count as 1/2 each. So in total we have 4 Cl minuses. For the octahedral holes, as we saw, there's 12 on the edges that count as 1/4, plus 1 in the center, which means a maximum of 4 sodium pluses. So if we have 4 Cl minuses, remember that the formula of sodium chloride is NaCl. That means all have to be filled. All right, or in other words, each unit cell has a total formula of Na4Cl4, which gives us an empirical formula of NaCl. So we're only going to balance the charge if we fill every single octahedral hole. That gives us exactly 4 chlorides and exactly 4 sodium pluses. So once we figure out which holes they go in, we have to use the formula for the compound to figure out if all of those holes are filled or only some of those holes are filled. And then finally, the coordination number for an octahedral hole. I should have given this on the table on the last slide, but that's going to be 6. Remember, octahedral means 6 coordinates, so there's going to be 1, 2, 3, 4, 5, 6 chloride ions that surround each sodium ion. So a coordination number of 6 when you have an octahedral hole occupied. All right, another example of a structure is going to be cesium chloride. So let's go down the periodic table from sodium to cesium and see how that changes things. If you look at the ionic radii of cesium and chloride, cesium plus has a radius of 174. As we saw in the last one, chloride is 181. So in this case, the two radii are very similar. If we divide the two to find the ratio, they come out to 0.96. That's larger than 0.732, which means we have to occupy cubic holes. All right, how many of the holes are filled? We have a simple cubic structure. So that means we have 8 corners occupied by cesium plus. Each counts as 1/8. So we have 1 cesium plus, and then for the cubic, or sorry, that should be the anion, which is Cl minus, sorry. And then for the cubic holes, we also have 1 of those. 1 maximum cesium plus, so all cubic holes are filled. And that'll give us 1 cesium to 1 chlorine. And then finally, for the coordination number for a cubic hole, the cubic hole is bounded by all 8 corners, so the coordination number is simply 8. All right, so we use the radii to figure out which holes are filled. We use the stoichiometry to figure out how many of them are filled. Again, in this case, we need to fill all the holes to balance the charge. Now, the last one I'll show you is a little bit different in that regard. So the last example I'll give you is zinc sulfide, which we also call zinc blend. And if we look at the radii here, zinc 2 plus is 60 picometers, so very small because it's a 2 plus ion. And then S2 minus is quite large because it has a 2 minus charge. If we divide these two, the cation, the smaller one divided by the anion, sorry, S2 minus in this case, that comes out to 0.33. And remember, if the radius is between 0.225 to 0.414, that's going to give us tetrahedral holes that are filled. All right, so in this case, the ratio lies between these two limiting values, so it's going to fill the tetrahedral holes. Now, I would figure out how many of them are filled. So in a face-centered cubic lattice, we have a total of 4 ions, as we saw, so there's going to be 4 sulfides. But for the tetrahedral holes, we have a maximum of 8. So we want to have equal numbers of cations and anions. The formula is zinc sulfide, just ZNS. So that means we're only going to fill half of our tetrahedral holes to make sure we have the same number of cations and anions. All right, so in other words, if we fill half of those tetrahedral holes, we get 4 zincs and 4 sulfurs, which has the empirical formula ZNS. If we filled all the tetrahedral holes, we would have too many zinc ions in there. It would be 2 zincs for every sulfur, which wouldn't balance the charge. So because we need the charge to balance, we can only fill half of these holes to balance the charge from the 4 sulfurs that occupy the face-centered cubic positions on this structure. Then finally, for coordination number, as the name implies, the tetrahedral holes have a coordination number of 4. So each zinc here has 4 sulfurs that surrounds it. And if you look closely, you'll notice that only half of the holes are occupied in this structure to give us the correct stoichiometry. All right, so that takes us to the end of ionic compounds. Again, that table is the most important part, and next time we'll start talking about some other properties related to phase changes.